Hello there, welcome to 9-2. We are talking domain of logarithmic functions. And I'm going to start off this lesson. We're going to kind of do an investigative kind of approach. We're going to consider three cases. So if we go ahead and consider the following logarithms, where the argument is positive, 0, and negative. We'll go ahead, we'll change these to exponential form, and then we'll see, okay, is our function defined or is it not defined? So here I have log base 3 of 9, okay, so that's 3 to the power of x is equal to 9, and our function is defined. I can go ahead and come up with an x value, right, that satisfies this, right, so where x is 2. Now, if our argument is 0, all of a sudden I have 3 to the power of x is equal to 0. Well, think about this. Can an exponential function ever be 0? Well, no, it has a horizontal asymptote at 0. Right? There's no value of x I can plug in, right? That will get the outputs to 0. So this is not defined. And then what if the argument is negative? And again, if I have an exponential function without any transformations given, there's no way to get a negative value. Okay, so it's important to note that a logarithm, log base b of a, is equal to n, where our argument must be positive. It must be positive or greater than 0, okay? So, since a logarithm is defined for positive values of the argument a, this means that the logarithmic function must be restricted to values of the independent variable x so that the argument is greater than 0. And that's just what we do in our steps. We'll take our argument, we'll set it set it greater than 0, set it strictly greater than 0, and then we'll solve the inequality. So we're going to be solving inequalities, and just some things to remember when we're working with linear inequalities and quadratic inequalities. If we multiply or divide by a negative, you'll see your inequality again switch, so don't fall trapped to that. And then when we're solving quadratic inequalities, what we're going to have to do is draw a number line. When we solve, we'll find our critical values, and then we'll have to test and see, okay, which interval gives us our domain. So here is our next example. Find the domain of the function. Use set and interval notation. Okay, so step 1, take the argument, and again, argument is the inside, right? What our input is, and we'll set it greater than 0. So 9 minus x is greater than 0, and we're going to go ahead and solve. So I'll subtract 9 on both sides. And we get negative x is greater than negative 9. We'll go ahead, we'll divide by negative 1. So here's Admiral Akbar. It's a trap, right? X is less than 9. We have to switch our signs, right? Okay, so this one was easy. Here is our domain in set notation, x, such that x is less than 9. Okay, and in interval notation, it is going to be negative infinity to 9, both parentheses. If you struggle with interval notation, what I recommend doing is just drawing a number line, and I can place 9 on it, and I want x is less than 9. So that's all the values this way, right? So this will tell you we're going from negative infinity to 9. Another way of thinking about it too is I've been told the inequality points as an arrow, right? So the arrow is going this way, so our domain's that way. Okay, next example. Oh, well, here's a practice. No, here we go. Okay. Example 2. We have the natural logarithm of 4x plus 7 plus 8, and we want the domain. So again, we'll take our argument 4x plus 7, and we'll set it greater than 0. We'll go ahead and solve. For x is greater than negative 7, so x divided by 4. X must be greater than negative 7/4. Okay, so again, as set notation, this is x such that x is greater than -7/4. And then for interval notation, that would be -7/4 to infinity. And again, they're both parentheses, right? I'm not equaling to that value. That would produce a argument of 0. We don't want that. Yeah, okay. So there are a couple of examples. I have a practice set for you. Please go ahead and pause the video, try this example. Okay, so hopefully you've tried this example. Here is the solution. Okay, did you remember to flip the sign? When you multiply or divide by negative, flip the sign. Okay. All right. Next example, and now what we're going to do is we're going to get into some quadratic examples. Now, quadratic examples are going to produce two critical numbers, and we'll have to go ahead and test. Okay. So step one is the same approach. We have 64 minus x squared. I'm going to set this greater than 0. Now, since this is a quadratic, what we do here is we switch to an equal sign, and I'll write it in a different color just to kind of note this. 64 minus x squared is equal to 0. And now I'm going to go ahead and I'm going to solve this. So I'll subtract 64 on both sides, giving us negative x squared is equal to negative 64. I'll divide by -1. We get x squared is equal to 64. And then we'll go ahead and take the square root of both sides, giving us x is equal to plus or minus 8. Okay, so what I've solved for, these are the critical numbers. These are where the argument is equal to 0. So again, we'll draw a number line, -8, 8. So here's our critical numbers. And what we want to do is I want to test this, okay? And remember, the best number to test, always, 0 and 1. There's, I guess, 2. But 0 is the best. So what we do is we plug it into our original inequality. I'm going to plug it in right here. So 64, take away 0 squared, which is 0. So 64 is greater than 0. Is this true or false? That is true, right? So that means that our domain is going to be positive in this region. So all values in here, this is our solution. On the outside, right, if I plugged in any values out here, I would get a non-true statement. Those are negative argument values, right, which our function's not defined there. So we have to go ahead and define this as our domain. So in set notation, our domain is the x values such that x lives between -8 and 8. So -8 is less than x, which is less than +8. Okay, and an interval notation, that would be -8 to 8. Again, parentheses, right? We're not including the 8s. Okay, they produce an argument where it is 0. Okay. All right. One more example. Here we have the natural log of x squared minus 20. Okay, so x squared minus 20 greater than 0. And then I'm going to go ahead and switch to an equal sign. And then we'll solve. Okay, so add 20. We get x squared is equal to 20. So x is equal to plus minus root 20, which is 2 root 5. Okay, so again, these are our critical numbers. So we'll go ahead and test them. So -2 root 5, +2 root 5, and we'll test 0. So when I plug in 0 into my logarithmic argument, we get 0 minus 20 is greater than 0. And this is false, right? Negative 20 is not bigger than 0. So we know that this is not the solution region, right? I'm going to have negative argument values here, and on the outside, I will have positive argument values. Okay, so that's our restricted domain. Okay, so sorry, I'm looking at my notes. Set. Right, and think about it like this. Okay, so x values such that x is less than negative 2 root 5, or x is greater than positive 2 root 5. Okay, so that's our set notation. And in interval notation, that would be negative infinity to negative 2 root 5. Union, right? Now we gotta cover this area. Okay, positive 2 root 5 to positive infinity. Okay. All right. I have a practice problem for you. Please go ahead, pause the video, and try this example. All right, hopefully you pause the video. Here is the solution. Okay. And I'm going to go ahead and stop the video here. I'm going to make a secondary video that has a couple more examples and practice problems. All right, catch you next time. Hey there, welcome back. 9-2, we're talking domain of logarithmic functions, and in this video it's going to be very, very short. I'm just going to cover a couple of examples of kind of weird examples of finding the domain of logarithmic functions, okay? All right, so here we are asked to find the domain of a logarithmic function in set and interval notation, and we're given the function g of x is equal to log of x squared plus 10x plus 25. So logarithms, their argument must be greater than 0. So I'm going to go ahead and I'm going to take the argument, and I'm going to set it greater than 0. Now, since this is a quadratic, I'm going to go ahead and switch to an equal sign, and then I'm going to solve the quadratic equation to find the critical numbers. So x squared plus 10x plus 25, that is x plus 5, x plus 5. Okay, and notice I have two of the same binomials. So x plus 5 equals 0 or x plus 5 equals 0. So I get two of the same solution, which is negative 5. Okay, so I have this weird case. I don't have two critical numbers. I only have one critical number at negative 5, and I have multiplicity. Now I'm going to tap into your knowledge about quadratics and parabolas. Now what we could have is we could have a parabola that has a vertex at negative 5 facing upwards like this. Okay, or we could have a parabola that is facing downwards like this. Okay. And I bring this case up because we're looking for values that will make our argument positive. I want the values to be positive. So what we would prefer is the case on top. I would prefer this situation. So I have values, right? So every single value would be a valid, I guess, domain value. Okay, because our argument would be positive except for negative 5. In the case below, all those values are going to be negative, so they won't be part of our domain, and we would be left with no values, right? And that'd be a pretty lame function because you can't do anything with it. Okay, so what we're going to go ahead and do is we're going to test two values. Okay, so I'll test 0. 0 is over here. So when I plug in 0, I get 0 plus 0 plus 25, so 25 is greater than 0. Yes, this is positive, so it's looking like this case where it's both positive. And then I'm going to go ahead and pick a value. I can pick, I guess, negative 6 is fine. So negative 6, if I plug that in, we get 36 minus 60 36 minus 60 plus 25, and this would give us 61 minus 60, right? Yes. Okay, so positive 1, so it's positive. Okay, so therefore, I know that our domain is everything except -5. Okay, so x such that x is less than -5 or x is greater than -5. Okay, and interval notation, that's going to be -infinity to -5, union -5 to infinity. Okay, so that's kind of the weird case number 1. The second case, here I have kind of a different type of a result. So let's look at it. X squared plus 16 is our argument. Okay. Notice how I don't even pay attention to the rest of the function, right? It all kind of doesn't matter. I want that argument to be greater than 0. So we'll go ahead and solve this. So x squared plus 16 is equal to 0, giving us x squared is equal to -16. Now, I'm going to go ahead and take the square root of both sides, and what I hope you notice is that we get plus or minus 4i, right? When I take the square root of -16. Okay, so what this means is that there's no critical numbers, okay? I have no values where it is 0. And kind of what you can think about it too, I mean, think about this expression here, x squared plus 16 is greater than 0. Isn't that expression always greater than 0? If I plug in anything into x, right, this is always going to be positive. So positive plus a positive is positive. So we're good. Okay, so what is our domain? Well, in set notation, it's all real values. So x such that -infinity is less than x, which is less than infinity. And in interval, -infinity to infinity. And there you have it. Okay? All right, I do have a practice problem for you because I'm nice like that. Here you go. Please go ahead and try this one. Okay, hopefully you pause the video and you've given it a go. Here is the solution. Okay? All right, and that is it. That is finding the domain of logarithms. Catch you next time. Peace.